Okay, today we're going to look at bolted and riveted, technically, although we're not going to do anything specific for rivets, joints that are loaded in shear, or what we'll say is eccentrically loaded, so that they have a primary and a secondary shear force on them. These are some diagrams from Shigley, 10th edition. This is in chapter 812, I think, is the section. Yes, 812. So the chapter starts out with a selection of pin joints, basically. These are showing rivets in them here, but it doesn't matter if it's a rivet or a pin joint or a bolt or anything, because we're going to ignore the clamping effect. So the idea that a bolt has a preload on it and there's this clamped region in the grip and all of that would enhance the holding capabilities of this joint in shear. We're going to ignore that effect and look at what happens if just the bolt or the rivet or the pin is doing all the work, all the shear load. And so we're going to look at that. So ideally, your connections that you design are going to be conservative, because there will be some effect from the friction between the two plates that are clamped together, so they don't slide past one another. There's some resistance there, but bolts come loose. Rivets, you never actually even know how much clamping force you have on those. The rivets they're showing here are more of the solid style rivet. Maybe you don't really run into those as much anymore. That's the old style. That's the ones you see in the videos of the guys on the skyscraper frames hammering on a I-beam somewhere. They're hammering in these old style solid rivets. They still exist. Probably what you're more familiar with is something like this. You have a rivet gun and some kind of little rivet like this. These rivets are probably more what you're familiar with. Now these, there we go. These little pop rivets, or sometimes they're called blind rivets, they work by, well, that one won't work. This one, you put it in the rivet gun, and then what's going to happen is, as I squeeze the handle on here, let's get this out of the way. Let's look at this again up close. So this stem here goes all the way through the rivet. This is the actual rivet. This other part is, well, I guess this part stays, but this part gets lost. It pops off after we install the rivet. But the rivet's right here. So when we pull on our rivet gun, we can probably see, it's starting to deform over here. Ideally, obviously, there's some sort of material that I'm clamping together, riveting together. It's not, again, you don't know how much force you're actually applying as far as clamping goes. But there's a head already formed on one end of the rivet, and then basically you're forming a shop head, or the head, by deforming the rivet itself by pulling this nail through it. And then eventually we'll get to a point where it pops, and then your stem is throwaway. So that kind of rivet is a little bit different than what they're showing here in your book with these solid rivets. There's other styles of rivets too, but the general idea with them is that you're not going to take them out easily. You have to drill them out, grind them off, grind the heads off, something like that. You're not just going to unbolt it. So we're going to stick with our bolts and nuts as our fasteners, but again, we're going to ignore any clamping force on them. Your book starts out in the Shigley book, and it goes through your typical failures. There's a bending moment, there's shear in the bolt, the member itself fractures. You've got some bearing stress here that's deforming the hole. You've got different types of a tear out based on shear and a tear out based on a tensile failure. And so it goes through those. Those are all pretty standard. We're not going to look at those. What we're going to look at is something a little bit more complicated, where you've got a beam, or well, it doesn't have to be a beam. You've got some member, and it is bolted to a support somewhere. And then the load it's going to be applied eccentrically. So here's our bolt group over here, over on this side, and load's way over here, and this load is causing at least two things to happen. One of them is just pure translation, so it wants to push the beam down, in the way I've drawn this load. It also wants to rotate the beam. So both of those, translation and rotation, are trying to shear these bolts. And we need to figure out how do we combine those two things together to size our bolts, figure out size the load. Maybe we already have the bolts, and we got to figure out how much load can go on there. So we got to do that. So what we've got here is an 18-inch beam with a 1,500 pound point load on the end of it, and a pattern of 2/4 inch bolts and a 1/2 inch bolt. So I've just drawn the bolt holes, but the bolts are the same size as that. Here's a bigger view of the bolt pattern, or bolt group. We'll call it a bolt group. And so I've done a couple of things here that make this a little different from what the book goes through. And typically these bolt groups are symmetric, they're in a rectangle or something like that, so it eliminates the need to do some of the steps, and it simplifies things. A lot of times they're all the same size, so they're all 1/4 inch bolts, or they're all 1/2 inch bolts, or whatever it is. So I took away those and made this a little more generic. So we have some symmetry here. It has an axis of symmetry along that line, but not that line. So we don't have full symmetry. Also, we have different size bolts, so that'll create a little bit of an issue too. And you do have to be careful with some of the book's equations, because let me see if I can find this. They do develop some equations that are specific only when, here we go. So this is page 449, and I've highlighted the diameters of the bolts are assumed equal. And they're talking about an equation over on the other page, which can't really get on the screen right now. It's equation B that we'll need when we're talking about the secondary shear. So that brings me to this idea of primary and secondary shear. The primary shear is the translational, when we're just resisting the translational force. And the secondary shear is going to resist, or be caused by, whichever way you want to look at it, the rotational. So that we have two different shear stresses that are being dealt with, or two different shear forces that are causing a composite shear stress, I suppose. And we have to add them together, and we have to figure out how are they even applied to these bolts? Does it matter if one is bigger than the other? Does it matter if they're different distances from some central location? And all those things yes, they do matter. So the first thing we have to do is we need to find the centroid of the bolt group. So in the book, a lot of times they have a rectangular pattern, and the centroid is just in the center of it. And that's not the case for what we have here. For one thing, we have different size bolts, and they're not in a nice rectangular pattern. They're in a triangular pattern, so we could probably figure out some centroid equations based on a triangular shape. But we've got this one big one and two little ones. So what you do is treat these, you can treat them as areas if you want to, or however you want to think about them, but just like you would solve a centroid of any other composite shape, you solve the centroid here. Now you do have to define an axis, where's your origin going to be. For this particular one, I did take advantage of the fact that we have symmetry along a horizontal axis. So I put my coordinate system like this. Let me find some color that'll show up. So I put the horizontal axis here. So that is my X. So that I have symmetry at least there. So I know that just by observing this, Y sub C is going to equal 0. These are all inches, if you can't see those. 0 inches. And then I did put the Y-axis. Made sense for me to put it right here. So y sub c is 0 based on that coordinate system. So when you're working on these on your own, you're going to have to figure out where's a good place for the origin. And it's not that there's a wrong place, it's just sometimes there are better places than others. So to me, this is probably the best location for the origin, but you could put the origin down here or wherever you want to and find the centroid of the bolt group. X sub c, so where, I know that the centroid lies on this line somewhere. I just don't know, is it over here, over here? I suspect it's closer to this bigger bolt than the two smaller bolts. And to do that, you just go in, X sub c equals the summation of AI xi. So this is the area of each part. I've got this part 1, part 2, and part 3. So I've gone ahead. I do have this worked out in MathCAD so that if we need to, we can get this information from MathCAD. So I've got the diameters over here of parts 1, 2, and 3. I've got their individual X centroids. And then here are their areas. So pi d squared over 4 for part 1, part 2, and part 3 for bolt 1, bolt 2, bolt 3, whatever you want to call it. Already have that y sub c is 0 by observation. You don't really need to calculate that. And then here we're working on x sub c. So back over here, here we have the area of each part multiplied. Maybe we'll make it more obvious that that's multiplied and then summed. Multiplied by the centroid of each part. So centroid, the x centroid for part 1 is on the x equals 0 location. Same for part 2. Part 3 is over here at 1.5 inches. And you multiply and add those together. And then you divide by the total area. So that's just a summation of all the areas. And we find that x sub c ends up 1 inch. So what that tells me is that if I move over 1 inch, I think I actually drew this to scale. Yep. So if I move over 1 inch right here, that's our centroid of our bolt group. Okay. So we have our centroid of our bolt group. So that's good. Now what we need to do is go back to our original diagram over here. Our point load that's causing the translation and the rotation is way over here, and our centroid is way over here. We need to apply this point load over here. So there's 2 steps to doing that, or at least 2 big steps. First, we just need to take the translational effect that this 1,500 pounds is creating and apply it over here. So that's really straightforward. That is just doing this. So there, it has the same effect of wanting to translate the beam downwards. So that's also going to create our direct shear. Okay. The other thing, though, we can't just simply move this point load over here, because this point load out at this moment arm is not only wanting to translate the beam, but it also wants to rotate the beam. So we have to account for that rotation. So we need to create a couple or a moment over here that has the same effect that this point load would have about this centroid. So basically we need to figure out what is the distance from our centroid. I'm going to draw down here. Maybe not the best way to actually draw that, but that's what we got. I don't like crossing the leader lines there. We need to figure out this moment arm. So we'll have to get some of these details from this picture. So I offset these 1/4 inch holes, 3/4 of an inch in, 0.75 inches in. We found that, I guess I didn't label it, but we found that x sub c is 1 inch further in. So I've got 0.75, 1, so 1.75 from the very end of our beam to get to the centroid. So if the distance from here over is 1.75 inches. If we go back to here, that's this distance. So the total distance length of our beam was 18 inches. So all we need to do is 18 minus 1.75, and we get 16.25 is this moment arm. And a 1,500 pound force. Whoops, put too many ones in there. And we need to create a 24,375 inch-pound moment at this centroid of this bolt group. So we need to put that on there. And it's going clockwise. So that would look like this. Clockwise, concentrated moment, and the value 24,375 inch-pounds. I guess you could use foot-pounds if you wanted to, but eventually I'll change this to 1,500 pounds instead of kips. Although over in MathCAD, as long as you put your units on, you can mix and match the units however you want to. MathCAD will take care of them. It's generally better to put them in the right units just for your own sake to make sure you have things correct, but MathCAD will translate between all sorts of different units. And so we have that here. Okay, the next, so that's step, well, I guess that's step 1 and 2. 1, we had to find the centroid, and 2, we had to relocate our point load, or whatever kind of load you have. We're just looking at a single point load, but whatever load you have, you need to relocate them to that centroid. So we moved the 1,500 pounds, and then we moved the effect, the rotational effect that it was trying to create about that centroid also. So we have these two force couple that represent the same effect as the single point load that was eccentric off to the side somewhere. But now they're applied at the centroid of the bolt group. Okay, so that's the first 2 steps. The next step is that we want to go in and we want to apply the direct shear, so the primary shear forces to our bolts. You don't just go in. So first, again, in your book, a lot of times they might give you an example where all the bolts are the same diameter. If that's the case, then you just take the shear force, or well, the translational force, and divide it by the number of bolts you have and put an equal amount on each bolt. So that's fine. We do not have that case because we have 1/4 inch and 1/2 inch bolts. So we can't just equally divide the force. What does end up equally dividing is the shear stress. So the shear stress on this larger bolt is the same as the shear stress on bolt 2, which is smaller, which is the same as the shear stress on bolt 1, which is smaller. Now 1 and 2 having the same area will have the same shear force on them and shear stress. They all have the same shear stress. So with that, let's go over here and just write that down. So again, I've got bolt 1, 2, and 3. And what we do know is that the shear stress in, well, not I, in 1 is the same as the shear stress in 2, which is the same as the shear stress in bolt 3. That may seem, you know, they've got some bigger ones and little ones, and so why does that work out that way? But remember that as parts begin to deform a little bit, then other pieces will take up some of the load, and so it does work out where the shear stress is equally or mostly equally distributed among all your parts. So that just gives us one formula. Now we need to be a little more specific about this because tau 1, tau 2, and tau 3 don't really give us the amount of information we need. So I'm going to rewrite these as in terms of that force, because what I want to know is the shear force on each one of these. So tau 1, remember a shear stress is a shear force over an area. You know what? I'm going to go ahead and go back and put a little prime marker on here so that this is showing that it's our primary shear. And on the secondary, when we get to those, the rotational ones, I'll put 2 little marks for secondary. So this is primary shear. The way I'd written it, it was actually the total shear, which is not true. So this is the primary shear on each bolt. So the primary shear force, now normally I use a V for shear force, but we're going to use F's, partly to match up with your book and partly just because that's what I already wrote down. So the primary shear force divided by pi d1 squared over 4. So I've got force over area, and this will be for bolt 1, equals same thing. Oh shoot, I don't have a way to erase that. That's a single prime. So this is a 2 pi d2 squared over 4, and then primary 3, so bolt 3, diameter 3 squared over 4. So that's the primary shear stress in each bolt written in terms of forces and diameters and things that we actually have values for. So that gives us some number of equations, but we don't have any constants here. I mean, we know the diameters and things like that, but we can't actually solve any of this. We need another equation. And the other thing that we do know is that whatever the distribution of shear force is, it has to react 1,500 pounds. So we have to have a total, basically, of 1,500 pounds pointing up to react the 1,500 pounds pointing down, if we just think about summation of forces in the y direction. And again, we're ignoring the possibility that there's any clamping force and frictional force between this piece and whatever it's clamped to, the wall back here that I've shaded in. So we do know that in addition to the shear stresses, primary shear stresses being equal, force 1 primary plus, so this is not equals, force 2 primary plus the shear force, primary shear force in bolt 3, we have to sum those together and they have to equal 1,500 pounds force. You're going to see when I show the MathCAD that I'm using over here, you really have to make the distinction between pound force and just pound mass. And so you'll see MathCAD has a lot of pound forces on it. Now I have a system of equations. Now, not all of these equations are independent equations, so I have to make a selection of them. What I do is basically I pick 2 of these equations. So this is actually a set of equations the way I've written it. I'll have to pick some out. And this one, I do want this one because it's the one that relates it all back to the 1,500 pounds. So I definitely want this equation and then some selection of these. This one is just these equations. So let's go look at MathCAD and see what I chose. All right, so here I have, this is MathCAD 15 again. And so this part, you're going to have varieties of ways to go about solving it. What I did is I put it in MathCAD so that I could take advantage of simultaneous equation solving in MathCAD. This particular one doesn't actually need any sophisticated things because you do have 2 equations or 2 bolts that are the same, and so that kind of makes it simpler to solve. You can do some substitution just by hand if you wanted to. But what I did, I have the given here, so it's telling it that it's about to enter a solve block. Then I have, now I didn't find a nice way to make the little prime markers on MathCAD, so I just put FP for the primary, and later on when we get to the secondary I did FS. So this is the primary shear force in bolt 1, primary shear force in bolt 2, and in bolt 3. These are just the initial guesses to seed the solver, so I just put them at 1 pound. Here, this equation is the same as this equation. So we know that they all have to add to the 1,500 pounds. Now in MathCAD, I did write it as equaling to some FP total, which somewhere I've defined as 1,500. There it is, 1,500 or 1.5 kips. Okay, and then here, these 2 sets of equations are these equations. So it looks like I chose the shear force in 1 over its area is equal to the shear force in 2 over its area. So I wrote that one out. That's this equation. And then I wrote out the shear force over the area 1 is equal to the shear force in 3 over the area of 3. So I wrote that pair. And so you can see it here. So there's my 3 equations. I have 3 unknowns. The primary shear in bolt 1, the primary shear in bolt 2, and the primary shear in bolt 3. And so I need 3 equations to solve those simultaneously. So I have the one that I know I want to have in there with the 1,500 pounds. And then I chose these 2 of the first equations set that I wrote. Well, technically the second one. And then this is just how you go about solving in MathCAD, or how I go about solving simultaneous equations in MathCAD. And we get these values. So 250 pounds, these make sense. These the primary shear force in bolt 1, it's just showing me, the green line is showing me that I've already defined that right here, and I'm redefining. It's just a warning that, hey, you've already given it some value already. Why are you giving it a new value? And that's because these were just guesses, and these are the actual values. So it does make sense that 1 and 2, the 2 1/4-inch bolts, have the same amount of shear force, and then the third one, the large one, has a different amount. And so it's 250, 250, and 1,000, which does add to 1,500. So let's put those on how they would show up on this diagram. That's going to start to get a little cluttered, so I'll try to keep it as neat as I can. But now these are the reactions to these forces. So these 1,500 and the 24,000 inch-pound concentrated moment need to be reacted. So if the 1,500 is pushing down, then I'm going to show a positive, or upwards, 250 pounds. I'm going to leave the units off just to keep it a little less cluttery, but they are there. This one going to be kind of hard to see, but that's another 250. And then on here we have 1,000. So these 3 are the primary shear forces on the bolts, and they react this 1,500 pounds, trying to translate, trying to move this whole thing down. They're not the only shear forces on our bolts, though. The secondary shear, remember, are that 1,500 pounds was also one to rotate our beam, so that needs to be reacted. That one's a tiny bit trickier, but it also goes back to the centroid. Let's see, how do I want to try and draw this on there? I'm going to use orange. It's about to get really cluttery, but if we have to redraw it, we'll redraw it and it'll be all right. So what you do is you go from your centroid to the center of each circle and draw a radial line out. So here and here, and this one's going to be on top of all that other, so you can't really see it, but there's a line right there. All right, these are the moment arms for this secondary shear. We're having to create a torque, basically, or a moment that reacts this moment. So these are the moment arms for each one of the bolts. So perpendicular to the moment arm, I need to draw forces that together, the 3 forces will, that sounds like a cartoon or something. Together, these 3 forces will react this one. So this one's going counterclockwise, so I'm going to draw these, or actually that one's going clockwise. I want to draw all the reactions counterclockwise. So I'm going to draw one, try to get it as close to, this is going to be a right angle. So this will be F, that's bolt 2, double prime. So this is the secondary shear force. Here, this one is actually right on top of this one. So I'm going to put it down here just to have room for it, but it is pointing upwards. So that'll be bolt 3 secondary shear force. And then over here, we're going to have something like this, and that'll be bolt 1 secondary shear force, where that's a right angle That's a right angle. All right, so it's like I said, it's going to get a little cluttery when you go to do these. You want to draw these diagrams pretty big, particularly if you're trying to draw all the stuff that's happening on here. So you can see a couple of things already. Some of these, like here's the primary shear on bolt 1, here's the secondary shear on bolt 1, they're actually kind of counteracting each other a little bit. Here I've got a positive y component, and here I've got a negative y component. So they're actually going to subtract from one another. Same thing over here. I've got a positive y and a negative y. Here, they're both adding. So they're both in the y direction. So I just add them together. These I can't just add together. I have to add them like vectors. So I do have to, well, first I have to figure out its magnitude. But I have to go and add x and y components or vector addition or whatever I'm going to do. I'm going to do x and y components. Here I can just add these two as soon as I figure out what this value is. So, but even though these add together, this one has much more area to shear than these. So it's not obvious to me where my real failure problem might happen. So got to carry on. Okay, so we got to figure out these magnitudes for the secondary shear forces. And it's similar to what we did for the first one, where we had the shear force equal to each other. And this is where you can get in trouble because your book has this equation right here. It's kind of blurry a little bit. But it's equation 857 where it has the secondary shear force and has it solved out. The problem with that is that all bolts are assumed equal. So we don't have equal diameter is what they're talking about, equal area. We don't have that. So what we have to do is, it says over here, right under that, it says if not, which is our case, one replaces the F double prime in equation B, it's on the previous page, with the shear stress, the secondary shear stress. So, which is basically the secondary shear force over pi d squared over 4. So I've done that. So I think we can write that. So this was all primary. And we'll do the secondary down here. Looks like my pen's fading on me. All right, so on the what we're trying to do here is, well, let's go ahead and do the equivalent of this first. So what that says is, so the equivalent in the primary was that all the individual forces added to 1,500 pounds. Over here, all the moments created by the secondary forces add to 24,375 inch-pounds. So we'll do the moment on 1 plus the moment on 2 plus the moment on 3 is equal to 24,375 inch-pounds. Now we need to rewrite these moments in terms of forces, distances, things like that. So moment 1 would be the secondary shear force in bolt 1 times R1. R1 is that distance, that moment arm. So this is R1. And then plus the secondary shear force in bolt 2 times R2 plus secondary shear force in bolt 3 times R3 equals 24,375 inch-pounds. Now R1, R2, and R3, we already, R1 is the length of that orange line. R2 is going to be the same length, just a different direction. And then R3 is the little one in there, from there to there. That's the easiest one to figure out because it's just this distance minus that distance, or this distance minus that distance, whichever, to 1 inch. So over in MathCAD, let's look at that again. Looks like that was just solving for the shear stress confirming from the primary. So it's just confirming that the shear stress does equal in each one of them. All right, here's where we are. Here is solving for R1. R2 is the same as R1, and R3 is just the 1.5 inches minus the centroid, the eccentroid. So it's half an inch. I think I said 1 a minute ago, but it's half an inch. All right. Okay. So what I've got here is basically just a hypotenuse of a right triangle. So if we look at this one, I've basically just gone in and created a right triangle right here with a base of, this is 1 inch. When we solve for XC, we found that that distance is 1 inch. This height is given over here, so that's the first we've looked at that, but it's just a given, 0.75. So in MathCAD, what I've got is the square root of 1 inch squared plus 0.75 inch squared is that distance, 1.25. Now in this case, if you look at that and you're good at ratios, you can see this is a 3, 4, 5 triangle and just do it, but maybe that's not obvious when it's decimals of numbers, but that is a 3, 4, 5 triangle. And so that's what you've got right here. 1 inch squared plus 0.75 inches squared. Take the square root. It's 1.25. All right. So what that tells us is that this one, you would do this. You could do the same thing, or just like by observation, that is also R1 is 1.25, and then just subtract. Subtract 1.5 minus 1 is ½ inch for R3. So you get your radius distances. Okay. So here, what I've got is I've entered a solve block again, and I've got the guesses, initial guesses for the secondary. So again, I didn't know how to put little double primes on the variable here, so I just did the secondary shear force in bolt 1. These are just the initial guesses. They're 1 pound each. Here's our moment equation. Actually, this is not the moment equation. This is calculating that moment that we did several steps ago. Here is setting that moment equation. Here's where we're at. So we just created this equation. The moment in bolt 1 plus the moment in bolt 2 plus the moment in bolt 3 equals that total moment, which is that 24,000. Now this one's showing 3.8, but it's just rounded off some. In MathCAD, even though it shows rounded numbers, they're all still there. So we don't have to worry about making it show more decimal or more decimals in that case. These equations we need to develop. So these are the ones from the book that said, so let me write down the book equation. Here's the book equation. This is equation B. On page 448. And equation B on page 448 says that F double prime A, or well, let's do 1 since we used ones, over R1 equals F double prime 2 over R2 equals F double prime 3 over R3. Now the problem again is that this equation in this form only works when the bolt diameters are the same. You go to the next page, page 449, and it says for unequal bolt diameters, replace F double prime with F double prime over pi d squared over 4. So you went from just a force to replacing it with a stress. And you can see where if you wrote this out with this in here and all of these were equal diameters, then they would just cancel out and you wouldn't have to worry about them. But we don't have equal diameters, so we do have to use this version. So you do have to be careful when you're particularly in, you're reading a textbook or whatever. Make sure you read all the surrounding text to make sure that you are using the equations in a valid way, because you could the text could have derived some of those equations based on some assumptions, like last week, or not last week, but a few lectures ago, where we had this thing. There were some really simple equations that would model this under certain circumstances. All the material is the same. And then if that's not the case, then you had to do a more complex version. In fact, there is, I didn't point this out, but there is a simpler curve fit equation that's like two factors that you can get a sort of close member stiffness constant value just with a curve fit equation. It's down at the bottom of that same page that those other equations were on. So, but again, it only works under certain circumstances. So this equation only works when bolts are all the same diameter. We don't have the same diameter bolts, so we have to use this version. So what that does for us is, here we are. I chose bolt 1 and bolt 2 to set equal to one another. So I've got the secondary shear force in bolt 1 over its area. So that's the secondary shear stress over R1. That's the moment arm for bolt 1. And the same thing for 2. And then I did 1 and 3. So the original equation just says that they're all equal. You can't write that equation. That doesn't do you any good. So you have to break it into two separate equations. There's actually more equations in there. I could have done 2 to 3 also, but then I would have too many equations. So again, I've got 3 unknowns: secondary shear force in 1, in 2, and then in 3. So I need 3 equations. One of which needs to be this equation that has the actual moment value in it, the 24,000 inch-pounds. So I've got that equation, and these two, I solve for them, and here are my secondary shear forces. They're pretty large. You know, I've got 7,300 pounds, 11,000 pounds. So I've got the secondary shear forces. Let's see if we can put those on our diagram over here. All right, I'm going to switch over to a smaller pin. All right, so F1, our secondary shear force in bolt 1, 7,386, this is pounds. 3, 11,820. And then bolt 1 was the same as 2, 7,386 pounds. Again, gets really cluttery in here. The different colors help. Drawing it even larger than this would help. Drawing multiple diagrams would help. Maybe you draw one with all your dimensions on it, and then one that has just the forces on it. But anyway, it does get cluttery, and there are some things you can do about that to make it better. All right. So now we have the secondary shear forces on all of these. What we do now is we need to combine the shear forces. These are just force vectors now. We need to combine them into a single shear force and calculate the shear stress on each bolt. So this is the easiest one because the 1,000 and the 12,000, 11,820 are both pointing directly up. They're in the same direction. I just add them together. That's the shear force on bolt 3. We already know the area of bolt 3, so let's do that one. So over here is the force in bolt 3, the total force in bolt 3. If we were to write this as a decimal number, we can see all the decimals there. So there is the total force, shear force on bolt 3. We already had the area of bolt 3, and force divided by area gives us a shear stress. So 65 KSI in this bolt of shear stress. Now you do have to be careful that you are keeping your stress types separate in your mind. So 65,000 sounds kind of low. You know, it's not that, for most metals that's not a problem, but we're talking about a shear stress, and we need to compare that to a shear strength, not our tensile strength that we've been using, or proof strength. Actually, for bolts we've been using proof strength. So let's just assume these are grade 8 bolts. We go look up how strong a grade 8 bolt is, and it turns out that the proof strength for grade 8 would be 120 KSI. So let's just make that assumption that our bolts have 120 KSI proof strength, but that is an axial strength. So our shear stress or shear strength is some fraction of that. And there's two major ways you can go about figuring out the fraction. You can either just use maximum shear stress theory and take half, so 60 KSI is our shear strength, or you can use distortion energy and do square root of 3, so the 0.557. I don't know why I put a 8 in there. I think I must have, I don't know. We'll need an 8, so that'll change our numbers a tiny bit. All right, 0.557. And so we did distortion energy on this one. The maximum shear stress is more conservative. So whatever fits your situation is what you need to do. And if I'm giving you a problem to solve, then I'll tell you which one to use. So in this case, it turns out we do have some factor of safety slightly over 1. And so bolt 3 seems to be okay. We didn't do any of its axial, how much factor of safety does it have against an axial load. It doesn't have much axial load on it other than the preload, but we didn't draw any loads that were really trying to create an axial stress in there. So we might think we're okay because, well, that one has the largest loads and they add together. These subtract and all that. So we might think we're okay, but you do have to be careful because even though this does have the largest shear force on it, it is a larger diameter. So even though these have smaller shear forces, they're smaller diameter, so we do need to check those also. So to go in and find those, what we need to do is figure out, basically what I would do is, how about we redraw, let's just redraw this one so it's not so cluttery. All right. And maybe we can draw it bigger too. A little bit bigger. All right, so let's just put this. This is bolt 2. So a close up for bolt 2. All right, so on bolt 2, we have a 250 pound direct shear, so primary shear. And we have a 7,386 pound secondary. So it's going to be off somewhere down here. And we need to add those two together. So it's really like method of joints or something like that. It's just a concurrent force system. And we want to find their, well, I guess it's not a concurrent force system because we're not showing the reactions to this thing. We just want to find the resultant of these two forces. We could do, something along the lines of a parallelogram to get an idea, but I didn't draw this the same scale as this. If this is 250, then 7,000 is way down there somewhere. So I didn't really draw it to scale. So the parallelogram is not really going to be accurate. What we need to do is, let's create our x-axis here. And then y will be here. The thing we know is that we did have this moment arm, right? R2. So it's over here somewhere. It's not the force, it's just the moment arm. Now, I should have drawn that a little better because that's supposed to be a right angle. So it doesn't look quite like a right angle, but it'll get our point across. Remember this triangle? It had this height 0.75 inches, and it had this base of 1 inch. Now, if this secondary shear vector is supposed to be perpendicular to this line, then what I do to create a perpendicular situation, if the dotted line has a rise of 0.75, then perpendicular to it has a run of 0.75 inches. And if it has a base or a run of 1 inch, then perpendicular has a rise of 1 inch. You just take the negative inverse, or well, the inverse reciprocal. Negative inverse, I guess, would flip it back around, but the inverse reciprocal of rise over run gives you the perpendicular line. So all I've done is taken the rise here and make it the run of the perpendicular line, and same thing for the run to the rise. Now I have enough information. Maybe you remember that the hypotenuse is 1.25. We don't really need that necessarily. But now I can go in and figure out the X and Y components of this secondary shear force, and then I can add them to the 250, which is just has a Y component. So that's what I've got over here. Whoops, get off there. Here we have the secondary shear force for 2. Well, actually, here's the secondary. This is the X component of the shear force. So this is this F, just shear force on bolt 2 in the X direction. So it is the X component of that secondary shear force. So it is just the X component of this line, the 7,300. So it is 4,400 pounds. The Y component is the primary, the 250, it's going up, minus the Y component of this guy. So minus the Y component is this part. So I end up with a negative. The negative doesn't really matter because I'll square them here in a second. 5,700 pounds. And then I add them together as vectors, an X component and a Y component. So the X squared plus Y squared, take the square root, is the resultant. So 7,200 pound resultant on bolt 2. But when I go to calculate the stress, so 7,200 pounds divided by the area of bolt 2, which is much smaller than the area of bolt 1, I actually get 146 KSI. Remember, my shear strength I had at 66 using distortion energy. I had 66 KSI, 69, or well, 67 KSI if you round up. But this is telling me I have 146 KSI of shear stress on that bolt. So my factor of safety is less than a 0.5. So now I'll probably have a problem. This is the same thing for bolt 1. Obviously, it's all the same. They're not always the same, though. You can't just say, but it's not because they are the same diameter. It's because of they do have the same magnitude for each one, and you're subtracting off the Y components from the 250. It is totally possible that you have other bolts somewhere that are the same diameter, but their components, primary and secondary, might add together, or they might, some might subtract, some might add. Some might add the X's and subtract the Y. You can't just say that since they have the same area, they will have the same shear stress. It's, do their primary and secondary components interact the same way? In this case, they do. They don't, not exactly. This one has a negative X, this one has a positive X component, but in the terms of shear, it doesn't matter which direction you shear. It's just what's the total shear force on the bolt. And they do have the same setup where they have a positive primary shear in the Y direction and a negative secondary shear in the Y direction. So that's what makes them the same. It's not the fact that they have the same area. So it would turn out that bolt 1 and bolt 2 are undersized. Bolt 3, the one that looked like it was going to be our problem, actually is okay. Barely, it had a 1.024 factor of safety, but it is okay, unless our guidelines call for a higher factor of safety than that. But bolt 1 and 2 don't even have a 0.5 factor of safety, so they might have some problems. Okay, so I think that will finish up all the topics that we're going to talk about on bolted joints. We'll move into, I think we do welded joints next. They have a similar approach to this. So you do weld groups. Obviously, welds are usually in some kind of line somewhere, but you still treat it sort of like this. We'll do that soon. Okay, I think that will do all that we need to do for today. We will see you next time.